Solving projectile problems using vectors. Example 1. This particle is projected at an angle of 30 degrees below the horizontal with an initial velocity of 8 meters per second. We want to work out the velocity vector. We take these directions as positive, working out the horizontal and vertical velocity components. Make sure to check the direction of the arrows at this stage. So the initial velocity is 8 cos 30 I, that's in the x direction, minus, because the arrow is pointing downwards, 8 sin 30 j, which simplifies to this. We could give the answer in column vector form as well, like this. Example 2. A particle is projected with an initial velocity of 5i plus 8j meters per second from a point A, which is 20 meters above the origin. The initial velocity in column vector form is this. We are taking these as our positive directions, horizontally and vertically. The particle is 20 meters above the origin, so its initial position vector will be 20j meters. We can work out the initial speed of the particle from the vector form using Pythagoras' theorem. So the magnitude of the velocity, or the speed of the particle, will be 9.43 meters per second. So we have 5i plus 8j, so starting here 5i plus 8j. From the right angle triangle, tan theta is equal to 8 over 5. We can solve this to work out theta as 58 degrees above the horizontal. To work out the velocity of the particle at any time t, we use the vector form of the Suvat formulae. So we are not interested in displacement, so I've crossed that out. This is the initial velocity in vector form. This is what we're after. The acceleration will be minus g, j meters per second squared, and we need t in our formula. So the Suvat formula without s is this one, v equals u plus at, and using the vector form we substitute our values in. So vector u is 5i plus 8j, plus, then we have the acceleration vector, minus g, j, or minus 9.8j, using g as 9.8 meters per second squared, multiplied by t, where t is a scalar. At the moment we have a j component here and another j component here. We can group like terms, simplifying, and then we get this. So here velocity is a function of time because we have t in our formula. So we have the vertical component because it's in terms of j, and we have our horizontal component. This form is far more useful than this, because when solving problems we may just want to look at the vertical component or just the horizontal component. Part C, we want to work out the time taken for the particle to reach its maximum height. So at the maximum height, is velocity equal to 0? Well, the answer is no, because velocity has a horizontal and vertical component. The horizontal component hasn't changed. It is what it was right from the beginning. The vertical component, though, at the maximum height is 0. At the maximum height, the vertical velocity component is 0, but there is still a horizontal velocity component. In our velocity vector, this is the vertical component, and this is the one that's 0. So we make that equal to 0, and we solve to get t equals 40 over 49 seconds, that's the exact value, or 0.816 seconds, to 3 significant figures. To work out the displacement from O at any time, so hence the displacement vector, again we use Suvat. this is what we're after. So looking at the Subat formulae, we need one without v. We've got no interest in v. So s equals ut plus half at squared. We substitute these vectors and t into this formula. And now again we've got a mixture of I and j components all over the place. There's a j component here, and there's another one here. And it would be more useful to group the I and the j components together, like this. So we have our displacement vector with the I component and j component. Now to work out the position vector from A at any time, we will use the displacement vector that we just worked out, but we need to take this into consideration as well. So the position vector is the sum of the initial position vector, which is 20j, plus the displacement vector s. If we add these together, this is from the previous formula that we worked out for displacement, and then simplify, collecting like terms. So all of the I terms are here and all of the j terms are grouped here. Part F, we're trying to work out the distance O to B. Now the position vector is referenced from point O, so we can take the vector and substitute in a value of time for point B, and we can work out the position of point B relative to O. So here's the position vector that we worked out earlier, and this is the value of t for time at point B, and if we substitute in, and we can see from here there's no j component, so that will be 0 anyway. You can put in the value of t in here anyway and it will just give you 0 for this part. So if the position is 15 meters, then that distance there is just 15 meters. For further practice, try these questions.